SwayamPrabha. Digital India. Educated India.
Hello, in this video we will start discussing about some design practices which are preferred in composite laminates. Until the previous video we have been looking at the mechanics of laminates, like how to relate the loads with the stresses and the deflections, as well as we also looked at the failure of the laminates. From here onwards we'll be looking at different design aspects of composites. We'll start with few design practices which more or less we have already discussed in the earlier videos, but in this video we'll try to collate all of them at one place. So we'll start with what is the design philosophy we need to follow while designing these composite laminates, and we will also see how this is different from the design philosophy we follow with metals. To start with, whenever we talk about design, it usually means how to avoid failure during the service life. Of course, there are many different definitions for design, and this is just one of it. But we are focused on this because this helps us to design a composite laminate which is lightweight, and basically what it means is we are designing it to the limits. Basically, it doesn't fail during the service life, but it fails maybe after the service life, or if the loads are much higher than the prescribed loads. But here the question is, what do we mean by failure? Because failure can differ based on which application we are looking at or which component we are looking at. So sometimes or most oftenly for metals, whenever we talk about failures, it is mostly yielding, because metals show a plastic behavior. So when we are looking at something which yields, it shows that there is a change in the shape and size which is abnormal, and therefore the operations can be compromised. But when it comes to composites, composites are not that brittle materials, meaning we cannot go by the yield criteria. And similarly, neither does composite materials, we can consider them as purely brittle materials, because depending on the matrix material you have chosen, and maybe with some of these fibers, there is a little bit of ductility as well. So composites are neither completely brittle nor completely ductile, there is something in between. So we need to evolve a design philosophy which is more specific to composites. We cannot blindly apply the principles or the philosophy we have been following with metals. So let's see, previously we discussed about the first ply failure, meaning at what loads the first lamina will fail in a laminate. And we also discussed about ultimate failure, meaning after the first ply fails, the laminate can still take load. So, but if you keep on increasing, after the first ply there is a second ply, and so on and so forth, and ultimately there is a complete failure, which we call it as the ultimate failure. So now the question is, when we are designing using composite laminate, should we go by the first ply failure or should we go by the ultimate failure? First ply is a more conservative design approach, meaning that the safety limits or factor of safety is much high, because the first sign of some damage, basically we say we will stop using this material. So this kind is quite commonly used in the aerospace industry in the previous days, because the knowledge of the way composites fail is less. But now that more and more research has been done on composites and there is a better understanding, there are few applications where people are also going by the ultimate failure, meaning since there is a gap between the first ply failure and the ultimate failure, so there is a time within which, if there is the maintenance is well planned, one can identify the damage and then come up with some repair mechanisms. So it is not always true that one should go with the first ply failure, because the difference in the loads for the first ply failure load and the ultimate failure load is sometimes much higher. So one should adopt strategies which can go beyond the first ply failure. Next, usually in automotive and aerospace industry, most failures occur due to fatigues. So these are not the static loads, but fatigue loads are the loads where we apply the loading in a cyclic fashion. So let's see how this fatigue failure is different for metals and composites. So when we discuss about metals, usually 80 to 90% of the fatigue life of the component is forms in developing a critical crack. What is a critical crack? So which means these are the number of cycles which takes to initiate a crack and then grow it slowly where it is in a stable fashion, because after the crack length increases beyond this critical crack length, that's when the propagation happens quickly. And as you can show here, this fatigue life for the crack propagation usually is between this 10 to 20%. This is the case in metals, but in composites, the fatigue behavior is very different. Here, even in the first 1,000 cycles, there are multiple damages one can see. So something like free edge delaminations or some fiber splittings, these happen. But that doesn't mean that the material is compromised, because the crack propagation in the composites happens in a more progressive manner. It's not rapid as though in metals, but in composites these cracks grow very slowly. What is the reason? Because earlier we have mentioned these fibers, they act as a natural barrier to the cracks. So let's say there is a crack growing in the matrix material. When it comes across these fibers, they hinder the crack growth. So now, fibers actually naturally hinder the crack propagation, and that for that reason the crack propagation is progressive. What it means is, while we design composites for fatigue failures, we should account for this progressive crack propagation, because majority of the life or the fatigue life of the component is in the crack growth. So it is better to take care of this while designing these composite laminates. And we'll also look at the steps involved in laminate design. Usually the first step is to choosing the materials. What are the choices we need to make? We need to choose what kind of fibers we are using. This choice depends on the kind of loads and the kind of temperatures or the service environments in which we expect these components or structures to operate. And later we also need to choose the resin which or the matrix material which binds these fibers. And a proper fiber volume fraction has to be chosen, because as we know, as we increase the amount of fibers, then the strength and stiffness increases. But then, because the cost is also proportional or the manufacturing methods are limited, then we need to make a choice what is the percentages we can go with. And the second step is to choose the optimum stacking sequence. What do we mean by optimum here? Because each stacking sequence will have its own stiffness and strength. We need to come up with a stacking sequence which, let's say for this application, we were looking at a minimum mass structure, meaning a stacking sequence which meets all the functional requirements or the design requirements with minimum mass. And depending on the application, maybe the way you define this optimum might change, but essentially what we are looking at is we need to define in each layer of these composite laminate, first of all, what is the composite lamina we have chosen. It could be CFRP, GFRP, or Kevlar, or maybe sometimes it is simply a metal also, because not all layers need to be fiber reinforced. One or few of them may be like only metallic sheets. In addition to that, we also need to choose what is the thickness of each layer and what is the orientation of each layer. So this actually is a very design optimization problem, and there are few softwares which are commercially available which help you do this, but otherwise it's definitely a topic for research, and people have developed optimization algorithms to help you come up with these optimum stacking sequences. So moving forward, we will now focus on different stacking sequences and see what benefits each of those stacking sequences give. So we'll start discussing about few design practices, and here we are focusing on the stacking sequences. So the first, it's always preferred if we can eliminate this extension bending coupling. What is this extension bending coupling? In other words, we are talking about the B matrix in the classical laminate theory, the ABD matrices, right? This extension bending coupling is the one which connects the forces with the curvatures, or it connects the moments with the mid-plane strains. So if this coupling is gone, it helps to simplifies the analysis, as well as the manufacturing also becomes easier, because it can create some issues during curing of the composites. So how do we achieve this is the question. This can be achieved, as we already discussed, by choosing a symmetric layer. So for a symmetric layer, we already showed that the B matrix goes to 0. Next, let's focus on how do we eliminate the extension shear coupling. Extension shear coupling, if you recall, is these components A16 and A26. What do they do? So if you apply an extension load, whether there is a shear strain or not is the question. Or if you apply a shear stress, will there be any extensional strains or not, is what these two terms decide, A16 and A26. So now the question is, how do we bring these values to 0? So the option we have is we can use a balanced layer. So if you recall earlier, what do we mean by a balanced layer? We are saying it should have equal number of plus theta plies and minus theta plies. The sequence might be anywhere, because for a matrix we said it is independent of the stacking sequence, meaning whether it is at the top, middle, or the bottom, the contribution to the A matrix doesn't change. But here specifically, we are focused on the balanced layer, and let me explain you why we are asking for a balanced layer. Earlier, you recall that Q16 for plus alpha is negative of Q16, or the transform, so with a dash of minus alpha. So if you have a pair, then this A16, because it is a summation of these times the Q terms times the thickness, these cancel out each other, and that's how we get this A16 and A26 going to 0. So next, the other coupling we are looking at is the bending twist coupling, which is from these two elements, the D16 and the D226. There are multiple ways which we can achieve this objective, where we can either try to avoid or bring these values to a small value. First way is to use the antisymmetric layer. Earlier we discussed about antisymmetric, saying that it is very close to a symmetric layer, meaning that for every layer at the top of the midplane, there is a corresponding layer at the bottom of the midplane with the same material and from the same distance from the midplane and same thickness. The only difference is, if the top one is an angle theta, the bottom one is at an angle minus theta, or the opposite angle. Why is this important? Again, with this same thing. So we are saying for every theta we have minus theta. And how does this help you to bring the D16 and D226 to 0? Again, the same thing. So the q bar component with plus alpha is equal to minus of q, sorry, I should write it as 16 or 26, so q16 terms. minus alpha. Since the q terms are have the same magnitude and a minus sign, these d terms also go to 0. So the d16, d26 go to 0. But there are other ways to achieve this. The other option is to simply use the 0 and 90, which is the cross-ply laminate. Why do how does this help to get the d16 and d26 to 0? Because we know for these laminas the q16 and q26 values are 0. Once these q16 and q26 are 0, then of course this will also lead to these two values going to 0. So the bending twist coupling can be avoided. There is one more way where we say we group the plus and minus. Mind you, this is slightly different from the antisymmetric layer. Okay, antisymmetric layer, we are saying they are equidistant. This pair is equal distance from the midplane. But here we are simply saying they are grouped, means the minus and plus are sitting next to each other. How does this help? Because again it relates to this value, the q16 plus alpha is minus alpha with a negative sign. So since let's see the expression for d16, we said it is summation of q16 times zk cube minus zk minus 1 cube, and this is 1/3. Okay. So what this does is it doesn't take the d16 values to 0, but since these q values are of equal magnitude and then these z values are very close, because let's say we are thinking about a laminate with 40 layers, and then if we are talking about adjacent layers, the z values difference might be very small. So what it means is this makes the d16 and d26 values small. It doesn't take them to 0, but it makes the values or the magnitude small. So the next practice is, it is prescribed to have at least 10% of the fibers in each of these four directions. These are the principal directions we have in a laminate: the 0 degrees, 90 degrees, and plus 45, minus 40. And for a moment, why don't you think why this is prescribed? So the answer lies with primary loads versus secondary loads. Uh, Let me explain what is a primary load and what is a secondary load. Primary loads is what we design for, meaning we know that a particular member, let's say something like this, is expected to have a, let's say this is a driving shaft, we expect that torsion is applied. So that is a primary load because that's what this is being designed for. But secondary loads are things which come once in a while. It's not uh, expected during the operation, but because of, let's say, a vehicle going on a speed breaker, then there is an occasional secondary load occurring. So these kind of secondary loads are there. So let's say if you design only for an extension load, you may say that okay, the orientation should be all 0. But then let's say occasionally there is a bending load, and then it might fail, or if there is a transverse load, it might fail because you haven't accounted to that in the design. So how do you take care of this? So we say, since there might be some secondary loads which can come occasionally, it's better to have some fibers in the perpendicular direction as well, so that just in case of those secondary loading scenarios or unexpected loading scenarios, this component doesn't fail. So we are protecting against those secondary loads. How do we protect? To ensure that at least 10% of the fibers are in 0 degrees and at least 10 are in 45, minus 45, and 90. And the last point is, we say we minimize the number of same direction plies stacked adjacently. So let me underline this: stacked adjacently. What we are saying is, so let's say we have again a sequence of 20 or 40 layers. and let's say out of these 20 or 40 layers, like 5 layers we have at 0 degrees. Instead of keeping all of those 0 degrees layers together sitting next to each other, it is better to spread them apart. And the reason is again to related with the crack propagation. So I think earlier we have discussed, if not, it decreases the chance of micro crack propagation across the plies. So let's say there are 2 layers. So for the moment, let's say in the bottom layer they are at 0 degrees, and at the top layer they are at 90 degrees. So and now in the top layer, let's say there is a crack which is propagating. So let's say there is a crack which propagates. So since currently the crack is propagating in the matrix layer. So matrix is a weak material, so the crack can propagate easily in the matrix. But once it moves from the top layer to the bottom layer, then it is uh, coming across these fibers in a perpendicular fashion. Then there is a hindrance for this crack growth. So ideally, the advantage we are getting here is, because now that we have changed the orientation from one layer to the other layer, the crack in the top layer cannot easily pass through in the bottom layer. Why is it so? Because of the different orientation of the fibers, now the fibers are coming in between the crack propagation. So this is exactly what we meant by uh, uh, so the micro crack propagation across the plies is hindered. So it's always a bad idea to stack all the same orientation plies close to each other. It's okay to have 2 or 3 plies. It's generally in a, as a rule of thumb, they say okay, one should not have between 0 to 0.8 mm. We should not be exceeding this value all with the same orientations. So usually for these it means close to 3 to 4 layers. Okay. So in summary, what we have seen in this slide is, we have shown different stacking sequences which will help avoid few of the couplings. So we started with the extension bending coupling, extension shear coupling, bending twist coupling, and lastly we have looked at the secondary loads, how to avoid failures for these secondary loads, as well as we are saying this stacking same orientations next to each other should be avoided. Again, this is related to the micro crack propagations. So in addition to this, we have few more design practices. But now we are focusing on the performance of the composite. So let's say we have different scenarios where we may need how to improve the bending stiffness. So how do we improve the bending stiffness? Usually, if you recall the mechanics of material course where we discussed about beam deflection, how do we increase the bending stiffness of a beam? Usually we change the cross section. Either we can go with an I cross section or a closed a hollow beam. The reason is because now you are moving the mass away from the neutral axis. So similarly here, how do we do that? We place the 0 degrees ply as far away from the mid plane as possible. Why are we focusing on 0 degree ply? Because when we bend this, and the top layer will have the maximum stress. So if we have a 0 degree on the top layer, it can, because we know the 0 degree has higher stiffness along the 0 degree or the x-axis, it can take most of the loads. And ineffectively what it does is it maximizes this D11 value, which is a component of the stiffness matrix, bending stiffness matrix. Next, let's see how do we minimize panel buckling and crippling. So there might be some applications where you are applying a compressive load and you are concerned whether how to avoid this buckling of these panels. The way to go is to place this 45 degrees and the minus 45 as far away from the midframe, either at the top face or maybe in the first two or three, either at the top or the bottom face. What it does is essentially it increases your D66 values. D66 values, as you recall, these are in the again the bending stiffness matrix, taking care mostly from bending twist couplings. Now let's see how we can design such that it can improve the damage resistance. So let's say if we are concerned about low velocity impacts, an example could be like a wind turbine blade, where we expect that there is a bird flies and maybe it hits the wind turbine blade. So how do we ensure that in these unfortunate scenarios, there is less or minimal damage to these composite structures? For that, we ensure that we place 45 degrees ply on the outside. Why is it so? Because it limits the fiber splitting. Because if it is the 0 degrees ply, it takes all the loads and the failure immediately happens at the top surface. But if it is a 45-degree ply, it transmits the load to the layers below it, so that there is less of the fiber splitting happening in the top layer. And lastly, let's look how to improve the in-plane shear stiffness. This we have already discussed when we were discussing about lamina. So there we showed where we have the highest in-plane shear stiffness. We showed that it is maximum at an angle of 45 degrees. So we should dominate this laminate with either 45 or minus 45 planes. So when we dominate it, naturally we have the in-plane shear stiffness to be high. The example again is like a driving shaft or where we plan to apply torsion. It's always good to dominate it with as many as plus or minus 45 plus. So these are the few design practices where we are focusing on the performance. So either we are trying to improve the bending stiffness, or we are trying to avoid buckling and crippling, or we are looking at how to improve the damage resistance or the in-plane shear stiffness. So let's summarize what we have discussed in this video. We first discussed about the design philosophy. How is it different from composite laminates? So we said for metals, most of it are designed based on yield stress, because plasticity is an important phenomena in metals. But whereas in composites, yield may not be a criteria, because the composite materials are neither completely ductile nor they completely brittle. So we need to follow with a different philosophy. And also when we discussed about fatigue failures, we emphasized that in metals it takes a long time to initiate crack, but once it is initiated and reaches a critical value, the time to propagate is less. But whereas for composites it's the other way, meaning the damages can start in the early cycles itself, maybe around 1000 cycles, but for the crack to grow it takes a long time, because the fibers in the composite act as natural hindrances for crack growth. And we also looked into the philosophy, should we go with the first ply failure or the ultimate failure load? We said first ply failure is a very conservative design, and which is okay if there is less confidence in the design of these materials. But if there is more confidence or more data available and there is a lot of experience we have using the particular composite material, then one can move beyond the first ply failure and try to take advantage of the extra loads the laminate can sustain beyond the first ply failure. Later we also discussed about few design principles or the design practices. First we looked at various stacking sequences, saying like there are some stacking sequences which can avoid some of these couplings we commonly discuss. And later we also discussed about few suggestions to improve the performance of the composite, like either the bending stiffness, or how how do we decide the sequence if there is a in-plane shear loads, or if we expect some low velocity impact damages. So this should summarize what we have discussed. These are only a few suggestions. Some of these suggestions, as you see, or if you go through the design, these are not like these should be met all the time, but we try to meet these suggestions so that we come up with a better design. But there are some instances where we need to break these rules, because depending on your specialized applications, some of these may not make sense. So one should be able to feel free to move beyond these rules, but you should have a good reasoning of why you are not following one of these practices. Okay then, thank you.